Thanks. I'm going to present our paper, Going Beyond Popularity and Positivity Bias, Correcting for Multifactorial Bias in Recommender System. I'm Jing. This is the joint work together with Harrie, Masoud, Herke, and Maarten. We are from University of Amsterdam, Radboud University, and Delft University of Technology. So the user interactions with atoms are subject to selection bias. That means these interactions are partially observed, the data is incomplete, and there is a systematic error in which is observed. So they could, for two reasons, the self-selection bias, where user choose to interact with certain atoms more often, or the algorithm bias, the atoms shown to the user are highly dependent on the algorithms. So maybe the algorithms choose certain atoms to show more often. So in the logged user interactions, we can usually observe the two typical forms of selection bias. That's popularity bias, where interactions on the popular atoms are overrepresented in the logged user interactions. In the plot, we look at the real-world Yahoo R3 dataset. So the left plot shows you the number of ratings over atoms. And they state that they have the biased training set, and the unbiased test set contains the user ratings on randomly selected atoms. And so you can observe the long tail distribution in the training set, and this usually shows as the evidence of the existence of popularity bias. And the second form is the positivity bias, where the high ratings are usually overrepresented in logged user interactions. So in the red plot, in the training set, the rating distribution may be highly skewed from the unbiased test set. The recommender system base their learning and evaluation on the user logged data. So what happened if the user interactions are subject to bias? Something we need to remember is the observed ratings only occurs on the examined atoms. That means the probability of an observed rating in the logged data depends on the probability of this rating and the probability of observing these interactions. What happened if we ignore bias? Let's take a simple example. We want to estimate the average rating of an atom based on the logged data due to positivity bias, where the high ratings are overrepresented. So this estimate is expected to overestimate the true rating. In general, ignoring bias could also lead to the over-specialization, filter bubbles, unfairness, and Masoud effects. So how to mitigate the effect of bias? A straightforward and simple way is that the probability of the true rating equals to the probability of the observed ratings divided by the observation probability. That is also the widely used methods, the inverse propensity scoring, is with observations inversely to their observation probability, so that in the expectation, the estimate is not affected by the selection bias. They could equal to or proportional to the ideal estimate. So with the bias estimation, then we can use the IPS-based methods to correct for bias. And the widely studied positivity bias and popularity bias actually are single-factor bias. That means the observation only depends on one factor. Could be the rating value for positivity bias and the atom for popularity bias. However, in real world, it may be more complex, where the observation could depend on both factors at the same time. That is the multifactorial bias we want to address in this paper. It can also be seen as a generalization of popularity bias and positivity bias. The existing work can be extended to the multifactorial bias. However, in literature, there is a lack of studies comparing IPS, the widely used IPS-based method, with using single-factor bias estimation against those use multifactorial bias estimation. We realized that there are two practical challenges. First, the consideration of multiple factors greatly increase the problem of data sparsity when estimating propensity or the observation probability for multifactorial bias. Second, the existing bias estimation leads to unstable performance when applied to the IPS-based debiasing method. So in this paper, we want to propose the method to correct for multifactorial bias and address these two practical challenges. The first part of our methods is to estimate the propensity for the multifactorial bias. That is, given a specific rating YUI and a specific atom I, what is the observation probability when observed this interaction? And usually there are two ways. One way is we can use machine learning-based methods like a logistic regression to predict this probability using the features in the data. And we choose to use Bayes rules with maximum likelihood because they are more robust. So we first use the Bayes rules to decompose this propensity into the conditional joint rating value and the atom probability, multiply the observation prior divided by the joint rating value and the atom prior. Then these elements can be estimated by using maximum likelihood. So for the conditional joint rating value and the atom probability estimate, we use their joint frequency in the logit data. And for the joint rating value and the atom prior estimate, we use their joint frequency on the small set of unbiased data. It's clear that the probability estimates rely on the frequencies of the combination of atoms and rating values in the sparse logit data and even sparser unbiased data. And this may lead to the estimated probabilities to be extreme small or even zero, then in the propensity is invalid. To address the data sparsity issue, we propose to apply the Laplace smoothing. For the conditional joint rating value and the atom probability estimate, we directly introduce the smoothing parameter alpha 1 to it. And for the joint rating value and the atom prior estimate, we first decompose it into the estimate of the rating prior, multiply the estimate of the probability, the atom to be the specific atom, given the rating to be a specific rating. Then we introduce a smoothing parameter alpha 2 into the second term. We found this will give us the most robust performance. With our estimated propensity for multifactorial bias, then we can optimize the recommendation methods using in IPS to correct for bias. Here we use the matrix factorization method. Then our goal is to minimize the following loss function, that is inversely weighting the difference between the predicted ratings and the true ratings in the observation according to their estimated propensities. And to optimize for the parameters, we can use, for example, the Adam optimizer to update the parameters together. However, we find the optimization is unstable in the experiments on the real-world dataset. So we proposed a solution based on the idea from alternating least square. We propose alternating gradient descent optimization, that is to alternatively update atom-related parameters and other parameters. I will show you later how it affects our methods in the experiments. First, our experiments look at several real-world datasets, and here I only show you the Yahoo Australia dataset. So the first research question we want to answer is, can the proposed multifactorial bias better mitigate the effect of bias in the logit rating data compared to the existing single factor debiasing methods? We compared our proposed methods with first 3 naive methods that ignore bias altogether, and then 3 debiasing methods. The last two methods are designed for the single factor bias, the popularity bias and the positivity bias respectively. And in the experiments, it's clear that our methods got the best mean square error performance. We focus on rating prediction task. So we got the best mean square error performance compared to other baselines. So this show us first, our methods can mitigate the effect of bias. Second, is better than the existing single factor debiasing methods. And interesting, we also compared methods, debiasing methods with using propensities generated from loss regression using the features extracted by the MF in the logit data. In theory, it can also capture the multifactorial bias, but it's not good as ours. Second, we want to know how the adoption of the smoothing technique and alternating gradient descent approach affect our multifactorial methods. So we first vary the smoothing parameters alpha 1 and alpha 2 and look at the mean square error on the test set. So the smoothing parameters start from 1 because if you set it to 0, the propensity may be invalid. And the best performance is when you set alpha 1 to 10 and alpha 2 to 2. And it's clear that as long as you don't set these parameters too small, you get the competitive performance. So the adoption of the smoothing technique is very useful for debiasing, for our debiasing methods. We also look at the learning curves tracking our multifactorial methods optimized by different optimization methods. The concurrent one is when you update all the parameters together using add-on, and the alternating one is our proposed methods. It's clear that our alternating methods give you the robust performance during training, and also can converge to a better performance in the end. We also have some results where we use different optimization methods for different debiasing methods. And in most cases, or more than half, it can lead to a better performance. Yeah, to conclude, we focus on multifactorial bias that is determined by two factors, the atom and the rating value factor. We propose a method to estimate and correct for this multifactorial bias. First, we have a propensity estimation methods for multifactorial bias using naive Bayes and maximum likelihood. Then we integrate these estimated propensities with an widely used IPS-based debiasing method to correct for it. To address the data sparsity issue, we propose to adopt the Laplace smoothing. And to increase the stability of the IPS optimization, we propose the alternating gradient descent methods. Yeah, thanks for joining.